thank you to Sean, who may be online, for inviting me in the first place. Thank you to Talia and Cam for stepping in. Really, really appreciate it. I've had a wonderful day. Admit I'm a little tired by this point, so hopefully the energy is still there. But I want to talk to you a little bit today about at lunch with some students, and the idea came up of like bio-inspired robotics, and is that an overused term and stuff. I titled this talk Microsystems-inspired robots because a lot of my work, like the whole time since I was a graduate student, has really bridged these two fields. So can we use kind of microsystems, ideas, designs, fabrication techniques, all of these things to improve robotic systems? And that can be both making small robots, but it can also be improving things like perception capabilities on larger robots as well. And so I think one of the interesting things we also talked about, I'm a fan of history. I actually did a minor in history of science when I was at Berkeley. And I kind of like to go back and see where some of these fields were really initiated. And this is an interesting thing to me, is that the world of microsystems, especially MEMS, these micro-electromechanical systems, has really always kind of envisioned robotic systems as part of it. So you go back to Richard Feynman's talk from the 50s, Plenty of Room at the bottom, at one point talks about tiny hands, building tiny hands, building tiny hands. Anita Flynn, who was a fantastic mentor of mine when I was a graduate student, was in Rod Brooks' group and had the first kind of idea of, okay, we can make little motors now, we can make little sensors, we can add CMOS, like, why don't we make a robot at these very small size scales? And in fact, the first MEMS workshop was sponsored by the IEEE Robotics and Automation Society. So it's always kind of been in the background, which I think is interesting. And I would argue that microsystems has already, to some degree, revolutionized robotics. And these kind of things, so a couple people talked to me about crazy flies today, and these small drones would not be feasible without this little MEMS inertial sensor that's providing this stability as you're flying around. So I think there's these really interesting interplays between the two fields that have kind of existed for a long time, but I would argue we have not done this. Like originally this kind of inspiration was, oh, I can make all these small things, I can make an ant, right? And I can have it crawl around and do some interesting things. This happens to be a trap jaw ant, which also jumps and does cool things, which I love as well. And we haven't done things like these skins and these, enough mechanosensing that we can actually kind of have these small moth-like creatures that can fly around and do so stably, even outside. And so I think we're still missing some of these things despite all of these kind of numerous existence proofs that we have out there in the world. And so we do look to biology a lot of the time for both inspiration, but also just, I know it can be done. Let's just figure out how to get from point A to point B. It might not be exactly how biology does it, but there are some interesting kind of things that we can tackle if we can solve some of these problems. So this is, as I mentioned, things that we've been working on for a number of years now. And so really kind of combining this expertise that we have in microsystems with some inspiration from biology to ultimately create everything from improved sensing and actuation on larger scale robots, as well as integrated small scale robotic systems. And so this is just a sampling of different things that we've done over the years. Everything from kind of very small scale microsensors, micro-actuators, locomotion at small scales. How do you move around if you're the size of an ant, ultimately? Different manufacturing techniques. So there's a lot of benefits in terms of using different materials. So a lot of soft roboticists that I talked to today, like bringing in some of those softer materials gives us benefits at the smaller scale as well. We've done a lot of work with jumping systems ever since I was a graduate student, looking at these kind of spring actuated systems. I love that work in general. And then even things down to wearable sensors for things like exoskeletons and biomechanics study, gait effectively, electroadhesives, distributed mechanosensing arrays, like all sorts of kind of fun things that we've looked at over time. Obviously, I'm not going to go through all of this for you. So I had to down select, which is always like, rather challenging. but I'm going to focus a little bit on both the mechanosensing, because I think that is an interesting kind of topic in general for a robotics audience, but then also some of the fun work we've been doing recently on small scale locomotion and how you want to locomote, especially legged locomotion when you are small. So I'm going to start with the distributed mechanosensing. And the general idea behind this is kind of this inspiration, right? You fly, even if you're in that lovely drone arena I passed by, you fly your drone around, a gust of wind comes by, and everything kind of crashes, right? So this is a big robot. It becomes an even more challenging problem when you're small, right? And you have this lower inertia, which is great. You can be more maneuverable, but you have to react to it fast enough. And so we wanted to kind of ultimately help solve some of this problem, ultimately, once again, by looking at some inspiration from biology. So these biological flyers, this is a hawk moth, Manduca sexta. This was from Tom Daniels' lab at University of Washington, like are incredible at reacting relatively quickly to disturbances. I mean, they can fly around outside. You can just sit outside, watch these bugs flying around. It can be even a little gusty. And they seem to do pretty well, right? I mean, I'm sure they're not perfect, but like they do way better than our engineered systems. And one of the hypotheses for this, and I apologize for the people in the back, that's probably small, at least with my eyes, is the general idea that you have these sensors kind of throughout the wings. And the hawk moth has hundreds of sensors, tens to hundreds of sensors across its wings. These are strain sensors, effectively, called campaniform sensilla. And the idea is that you're starting to get interesting deformations from your wings that you're not expecting if you hit a gust, which can help you do this kind of feed-forward response before your body inertia starts to be affected ultimately by the gust. It's one of the hypotheses. And so the question that we had was, can we demonstrate some of these same kind of enabling principles of this kind of fast sensing and response in our engineered systems? And so we started with the same kind of idea that I'm showing here of the idea of kind of incorporating strain sensors into a wing. And if you look at some of the work that existed kind of around the time we started, this is some of Sean Humbert's work. This is a bear. You don't want to fly anything around with this. Like, I mean, there's wires going everywhere. These are just foil, like piezoresistive probably, or piezoresistive strain sensors. They're brittle. They're going to come unsoldered. These things are going to crash no matter what you do, right? This thing, nobody ever wants to fly, basically. So one of the ideas that we started with is, can we create these kind of robust sensing skins that would allow us to detect the kind of deformations that we want, do so ultimately quickly enough that we can do kind of closed loop control on these systems. And so this was work that we started a number of years ago, and this is primarily Hee-Sup Shin's work, who's now a professor at University of Missouri. And the basic idea of this is we're creating a capacitive strain sensor. So this is a sandwich of two conductive elastomers with a dielectric in the middle, so it creates a capacitor. And so if I strain that, right, my gap is going to change, my area is going to change, and I'm going to get some change in capacitance. And the benefit of doing kind of the microscale work here is that the smaller I make this gap, the more sensitive my sensor is, so I can detect small strains. And by making this out of this elastomer material, not only am I making myself more robust to crashes and that sort of stuff, but I also get very large strains, which is typically a very challenging problem for sensing in engineered systems, is getting this high dynamic range, right? It's something that's a classic thing that biology does incredibly well, and we do not do well in engineering. So being able to detect small signals as well as very large signals. So this was the idea behind this. And we pretty quickly kind of moved things out of the clean room. So I do microsystems work still, but a lot of it we don't do in a traditional clean room setting these days. In this case, we realized pretty quickly we could use a fairly small kind of end mill, very traditional kind of milling process, basically etch our sensor into an acrylic sheet, pour in the conductive elastomer, pour some dielectric on top, peel it out, pour some more dielectric, and now you've got a sheet of rubber, basically, with sensors kind of embedded throughout it. So this is the basic idea of these sensors. These are these interdigitated combs. So you have this kind of gap kind of running throughout the structure there. And so these things are, they're made out of rubber, they can stretch, they can bend, they can do all of those things. And so we can then integrate them into this kind of strain sensing skin. So we went through multiple iterations of this, and I'm happy to kind of talk about it. But one of the things we quickly realized is that ultimately, we want to kind of design systems that are not just collecting data all the time. Like, I don't care about the strain in my wings the vast majority of the time when it's not really changing. Like, I really only care about the data when things are changing. And so we kind of built this more distributed sensing system in this particular case, where we have a handful of these sensors kind of connected to its own little electronics that would then be able to kind of process any kind of changes that we might be looking for, and only then send things back to the autopilot. So it's basically kind of working on sparsity of data. I had we had 16 strain sensors across one wing, so 32 total. If I'm collecting all that data and then trying to crunch on it in a fairly small UAV, like that's gonna be quickly overwhelming from a computational standpoint. So I want to design something that I can react to much more quickly, ultimately, and close the loop in these systems. So they are reasonably fast in this approach. So we can look at just a ring down for our wings. So what this plot over here is showing you, if I can find my little arrow here, this is the displacement of the wingtip. These are the sensors at the base of the wing, are obviously going to have the highest strain response. But you can see the sensors even at towards the tip of the wing also are still picking up that ring down, and doing so with a relatively high signal to noise ratio. So we're able to collect some good data from these things. We were also able to actually fly this around. So this is with our collaborators, Sean at University of Colorado. I'm going to see if I can pause it if I'm fast enough here, so you can actually see the sensors as it flies over. So you can see the sensors kind of underneath the wing there. So in this case, this was an older array. It had 14 sensors kind of on each wing. But we were able to kind of collect data from this in flight. So one of the interesting things, and this was one of the hypotheses going in, was that these strain sensors on the wings could ultimately encode accelerations, right? And you might think, well, okay, you just showed me, I have this wonderful MEMS accelerometer. Why do I need these kind of things? Part of it was trying to understand even how the insect kind of encodes accelerations. And like a lot of fruit flies and other kind of fly species actually have these effectively vibratory gyroscopes that they're using to kind of detect ultimately kind of changes in rotation and the like. In this case, this shows capturing Z acceleration as I kind of go through a heave motion, and the wings are responding to that. And so the other thing it shows is that one sensor on its own here, it's pretty noisy, not all that helpful. Like, how am I interpreting data from that? But if I look at the kind of full array, right, I'm actually doing some spatial integration effectively over that array, I can get a really kind of nice picture of what's going on. And actually, if you look at some of these points, you start to see some of the changes kind of right before the acceleration changes. So that's one of the things that we're hoping to look at ultimately a little bit closer going forward. So strain was really interesting, but one of the things we thought about is, like, I'm flying around, like, strain is helpful, but what if I'm not a nice fixed wing aircraft like this? I want to ultimately be able to tell something about flow as well, right? Very important as you're actually flying. And so this actually came out of some previous work that we had done with Mitra Hartman at Northwestern on whisker sensing. And so I was like, well, we can take these little whisker sensors that we made as part of that project, slap some fins on them, and now voila, they're flow sensors through the air. Like, little did I know actually how well it would actually work. Sometimes you have these kind of serendipitous kind of things in research. So the basic idea behind this was we wanted a high bandwidth sensor. So we used kind of magnetic field transduction here. So there's a little magnet kind of underneath this whole structure, little magnetic field sensor that you can buy like very cheaply, 3-axis magnetic field sensor, and then you have a spring suspension of some sort. And so as you're moving through a fluid and you have that drag force acting on your sensor, right, you'll get a rotation here, which you can then back out and actually calculate what kind of flow you're seeing on that sensor. And so we did do some wind tunnel characterization of this and everything, did some basic simple optimization to try to make it more responsive to flow sources than inertial signals. But one of the cool things I loved is that we had just started this kind of collaboration with folks at Washington and MIT and John Howe's lab. I was like, you know what? We have these flow sensors. I think we could make them flow sensors. Let's pop them on some quad rotors, fly them around, and see what we get. So this was thankfully right pre-COVID. So January, my students flew out to MIT, put some of these sensors on one of their, in this case, 6, hexarotor aircraft. So they have a couple sensors here to get flow in 3D ultimately. But what you're seeing in these plots here is the Vicon captured velocity, and this was in an indoor environment, so there's no wind here, right? But a Vicon system, and this is the data from our magnetic field flow sensor. And so what it's showing is that we can capture really well kind of velocities in these systems, which anybody who works with drone and trying to state estimation on a drone, really lovely to kind of have that additional velocity signal and not rely entirely on your accelerometer or your inertial sensor of some sort. So this was one of the ideas behind this. What we've done a lot of recently that I don't have a lot of information here on is really thinking about, okay, I can fly this indoors and get velocity information. I can kind of hang out outside and get wind information if I'm kind of hovering. How do I get both, right? And so ultimately that actually comes down to how you set up arrays of these sensors in an interesting way, or even one of my favorite parts, how you shape the sensor so that different kind of drag profiles are different when wind sources are coming from different directions. So sometime later, I'll throw in some slides on that once some of that stuff is more published, but I think there's some really kind of exciting things here. You never see one whisker on an animal, yeah? There's always a group of them, right? And there's always like really interesting kind of interactions that you get through the array of sensors that you have. And that's one of the, I think, the exciting directions. The other thing we've been working on, that was a fairly big quad rotor, right? But these are super lightweight systems, they're small. So we recently have put these on small quad rotors. This is a Crazy Fly right here. We've designed the sensor to be far more robust now. So it can fall from the top of that outdoor drone arena, crash, and the sensor is fine. Like, this is, I think, one of the kind of cool new things we've been doing with this. I have a PhD student, TJ, who I forgot his picture here, but is really interested in kind of outdoor, kind of climate-related things, environmental monitoring type applications. And so he was really interested in being able to ultimately find a chemical source or an odor source, for example, the classic kind of source localization problem in robotics that people have been working on probably since the 60s, effectively. And so in this case, the general idea is much like visual servoing that you might do with a camera. Now you're doing wind servoing with this flow sensor. So you only need one flow sensor in this case, right? It's on this small quad rotor, and as soon as you get into that wind field, right, no matter, we can do like a little casting thing to find the flow source. As soon as you get into that flow source, you can immediately zoom straight toward it. Right? And so that's what some of this data right here is showing. Like, it might squiggle around to find the flow source, and then whoop, it's able to immediately kind of find the source of that flow. In this case, it was a fan and an open beaker of ethylene. We did go to environmental health and safety. It was all kosher. But I think this is kind of also a really exciting direction, that you can do this so quickly, so easily. Especially right now, the way people do this is with multiple drones. They're trying to kind of understand how they're all reacting to flow to try to get a picture of what's going on in a particular environment. I think you can do that much more easily with this fairly simple sensor. So that's kind of, okay, we can sense things like strain, we can sense things like flow. But one of the things that we consistently run into, especially on that fixed wing system, was this idea that I'm collecting a lot of data that I don't need ultimately, right? And I want to kind of reduce the amount of data, go for this kind of sparsity in data, sparsity and kind of timing of things. And I want it to be when I care about what's happening, right? And so This is something that's become much more popular recently in the world of vision, right? This idea of event-based cameras, where I'm only looking at kind of changes in illumination over time, and I'm not sending back, reams of data when nothing's changing. And we've been thinking about for quite a long time the kind of mechanosensing equivalent of that, right? So how am I actually, and your own sensors are very similar in behavior, and the moths as well. So this was work with Tom Daniel and Bing Brenton at University of Washington, and Ali Weber, who's now Swarthmore, one of the small schools in Pennsylvania. I forget exactly where. But the general idea here is that if you are having this hawk moth fly around and you're measuring the output of one of the strain sensors on its wing, effectively what you're showing in this is that only when you get this particular strain pattern on the wing do you get that neuron firing effectively. So only when something of interest to the moth is happening do you get this kind of event effectively. And they were able to show that you can kind of play around with frequency and width of these signals and get this kind of cool, what they call kind of neural encoder of this spike trigger average right here. So once again, kind of abstracting the basic principle, what I want to think about is when something is changing to the point that it's, something that I need to really pay attention to, can I get that as a kind of signal in my system? So in this case, we looked at strain sensing again, and here's your traditional strain sensing path. Even for our capacitive sensors, it was not so different, right? You have your strain sensor, it's going into DAC, you have to condition it, you have all these thermal things, all sorts of issues. Then you have to put it into software and try to really understand what that strain is even telling you, right? So the basic idea behind this kind of sensor, this kind of event-based sensor, strain sensor, is that when you exceed a particular strain threshold, and this can happen in tension or compression, then you effectively get a switch that closes. And then you get a change in your signal, which, especially if you're doing kind of a cyclic event like flapping, right, can be really helpful, just the timing of when that transition happens. Right? And so the timing is something that even on a very simple microcontroller, I can measure exquisitely well, right? And it can be hard to get like a less noisy signal on an ADC or something like that. So we started making some of these things. So this was Reagan Kubitschek and Sukjun Kim's work. And the basic idea in this case is we use a nanoscribe, basically a fancy 3D printer for the microscale. We sputter metal on top of it, so it's minimal cleanroom exposure here, but there is some cleanroom usage. And we can print a lot of these kind of wherever we want on this flexible thing that we're calling a wing. You can effectively design them to get the kind of threshold that you want. You don't have to design them all to be the same, right? But you're printing them where you want them as well. And of course, so this shows the printing process and the sputtering. Right? Using the 3D printing, you can create these kind of electrically isolated but mechanically connected pieces, which is really nice. This is a very nice, pretty wing that Reagan made at one point. Here's a very simple wing. We use this kind of plate-based. It's a little PET, I think 7 mil thick. And we use this because this is something that was previously used in some of the analytical techniques in looking at flapping flight. And so in this case, we have a number of these strain sensors. In this case, maybe 6 strain sensors kind of across the base of this wing. And the basic idea behind this, right, it's just a switch, kind of like a push button you'd have going into an Arduino or something like that. You have some pull-up resistor, and you're going to get a change on the digital input, which you can capture with an interrupt or something like this. And so if you're flapping up and down, you're going to get this square wave. And based on whatever your threshold is or where you're located on the wing, you're going to get a different duty cycle for that square wave. They should all have the same frequency, which is the flap frequency. So this is a case where we designed sensors with 3 different thresholds. I apologize, it's a little faint here. But what you're seeing in this is 3 different duty cycles, effectively, for those square waves. And we were able to show as well that you can detect disturbances with this, right? So if I'm flapping up and down and I have strain sensors on both sides of my wing that are designed to close at the same threshold. As I flap up, they close together. As I flap down, they open together, right? And this should be happening. If I get hit by a gust, now all of a sudden that timing changes. So you can imagine just putting an XOR gate on this, right? And you've got an immediately kind of spike that's coming out of the system, like, bloop, something's happening. So this is the idea behind some of this kind of sensing work. We have also, since this, actually flapped and rotated, and you can actually, from just these digital strain sensors, pick up yaw rotation rate, right? Which for me is pretty incredible. And so I think there's some really kind of interesting kind of stuff coming from this in the future as well. And I think for me, it's a kind of an open question of like, how am I like encoding this information very differently, right? I don't know, it's easier for me to visualize this kind of analog strain field. And now I have this very time-based thing. Like, how is that information being captured? Why is it like less information in some fashion? Like, what can I ultimately leverage about this to do something about it? So we've also done a couple other kind of styles of these switch-based sensors for acceleration and for flow as well. So I'm going to pause for a moment right here. So we have, a number of different ongoing things going on in this space. So in this case, I mentioned kind of the digital logic that you can use when you have these switch-based sensors now. So you can kind of embed some of the decision-making and the logic just in the way you design your sensing system or your sensing array across these wings. This is an OR gate right here that's being demonstrated. We're also taking, some of the things that we've learned from a lot of the strain sensing kind of to some biomechanics stuff as well. The rest of it's going to be very locomotion focused, so I wanted to kind of take a moment here and see if anybody has any questions on this aspect, on the sensing, before I move on. Yeah.
So you've showed us these really cool, like one is basically like a mechanical intelligence way of sensing and kind of filtering almost.
Mm-hmm.
One was sort of an onboard computation.
Mm-hmm.
And both allow you to reduce the complexity of the data that you are getting into kind of your central controller.
Right.
When would you want one versus the other?
It's a programmability thing. It's how you want to change over time. So the physically kind of programmed switch structure obviously is a little harder to change over time. I can change it over time. I think there are some kind of exciting ideas that I have, especially on some of the biomechanics stuff of like effectively pressure sensing that I can then change that pressure threshold like over time so I can adapt to a particular person, set those sensors, effectively set them up so that they space their kind of transition as far apart as possible to help me classify the kind of thing that I might want to classify. So for a gait, like a normal gait versus kind of a wonky gait that you might get after ACL surgery or something like that. So this is something we've looked at for the flapping wing is how do I place sensors or design sensors in a way such that I can, as easily as possible, classify what might be happening in that system. And so a lot of that comes down to placement, design, et cetera. There's a lot of kind of interesting things there. The more kind of onboard computation, obviously, there's a little bit easier just from a software perspective to adapt what I'm looking for over time. I'd say that's the biggest difference. I think you can do it for these other systems. This is just a little more challenging. Mm-hmm. Any other questions on this? You can also ask questions on sensing at the end, but yeah.
So it seems like this system actually lends itself to a surprising degree of scalability, which is a problem that you often encounter with these small scale systems that are hardware driven. Provided, in my mind, at least if I were to be the person dictating how this works, which I'm obviously not, you did enter the clean room. And so yeah. Is there a reason that you're like not entering the clean room to like go full MEMS with this approach? And is it just that it doesn't need that level of granularity to get the information that you need? Or
you're talking about for these kind of sensors and the like?
Everything from here onward, yeah.
Yeah. So these sensors, there is some benefit to not going into the clean room. I don't think I don't have a side view here. Oh, I guess I did have it in this. So we do utilize kind of the 3D nature of these sensors as well. This little riser, this height right here for the strain sensor actually matters in how you're kind of transmitting that strain to the structure itself. So the 3D printing is useful kind of from that perspective. It opens up our design space much more than we can do at the small scale, at the microfabrication level. We cannot still get the feature sizes that you can at the small scale. So if we could kind of translate your design to this kind of extruded 2D design, then I think from a, if you want to make a lot of them, right, that would be the way that I would go still. We don't care to make a lot of them yet.
But you don't need to.
I don't need to yet. And I think that this is something that I mentioned in a previous thing that I did. I love this technique from a student perspective. Like, anybody here do anything in the clean room? Like, okay, it's a nightmare. So it can take you months to even just be able to step foot inside the clean room, right? Just from all the training that you have to do. And then like you have to learn each piece of equipment that you want to do. The equipment's down a lot. Like there are wonderful benefits to working in the clean room, but from a student perspective, it's really challenging. So these kind of things you can iterate on in a day. Right? You can design it in CAD, print it, sputter it, test it, and do something else the next day. It is super wonderful. Like I'll show you that with kind of one of the locomotion robots later on as well. I had a student come in for a summer program at one point, and he was working on this little microscale delta robot. So anybody familiar with the kind of pick and place delta robots? We did a tiny one that's about 1.5 millimeters in diameter. Junior was able to come in, do like 8 versions of this in a summer. Like, it's a very complicated design actually, but I think it's a huge thing for actually speeding up this kind of work.
I appreciate your candor with the practicality of keeping things out of the.
Oh yeah. I mean, there are benefits. There are huge benefits to going in the clean room, but yeah, for a lot of the things we do, we don't need to take advantage of those benefits. All right, I'm going to switch modes into the locomotion side of things and kind of tell a little bit of a different story here as well. So this is something I've been fascinated in for a while, right? You watch these like incredible videos, and I'm no different from a lot of people who do robots that kind of overlap with biology and robotics, where you watch this and you're like, well, I can't make that. It's kind of incredible, right? This whole collective is working together, like they're doing these cool things. But even just the locomotion, now I have to be an ant that crawls over these other ants. That's hard on its own, like. And so I think that these small locomotors, like locomotion at big scales is fascinating. Locomotion at small scales for me is just even more fascinating and challenging. And so they have all these extra challenges around energy, control, computation, size scale, all of these different things that I think are a big challenge. So, ultimately, the question we go into this with is how can we ultimately design our robots to help with these kind of locomotion challenges at these small scales? In some sense, unlike the big robots, right, we can't stick it all in computation. We have to think about kind of other methods that might help us out. And so, this is interesting because I've been thinking about this since graduate school. And in microfabrication, we've typically had these 2 design spaces. I can change the material and I can change the layout kind of geometry of the mask. In robotics, we've typically had these 2 design spaces of the control and the geometry, right? I can change the links in my robot arm. I can change the control of it, right? These are the kind of 2 different things that I have at my disposal in general. And so if I think of the computational control side, all the cool, stupid robot tricks that you see in YouTube videos now, right? All computational control, really impressive stuff right now. I would love to be able to take more advantage of that at small scales. At small scales, like often we're leveraging, this is the other side of things, even at large scales, where you're leveraging kind of the passive dynamics of your system. This is Steve Collins's old work on this kind of passive dynamic walker, right? And you're able to do this like really efficiently really like low control kind of bandwidth, but you're not going to be doing backflips or anything like that, right? I would argue we also have this kind of third design space now in robotics that we used, I think of from a microfabrication perspective, but I don't think is traditional in robotics. Maybe you would call it traditional at this point, but the kind of materials that I'm using here, like I can use a more elastic material, a more viscoelastic material. I'm going to get different behaviors for those different things. So I want to talk a little bit about how we're using different combinations of these to help kind of locomotion in small scale systems. So the first question is looking at how material choices of my legs can ultimately help me locomote perhaps more quickly and more stably over different systems. So this is work that was with Jonathan Clark at Florida State and a former student and postdoc, Ryan St. Pierre, who's now at Buffalo. So the basic idea here is a traditional slip model of locomotion, right? I look at my inertia and a spring leg. We're adding some damping to that because I can use viscoelastic materials that add some damping to my leg, right? And looking at how these things are able to locomote in terms of speed, stability, and things like cost of transport. So in this case, we were interested in small scales, but we were also not interested in, spending all of Ryan's time kind of trying to integrate small motors and tiny wires and a little microcontroller and a battery and all this stuff. So we started off with kind of magnetic locomotion. So in this case, we have magnets in the hip here, right? And for the big one that I'm going to show you right now, we actually had a rotating magnet kind of underneath it that kind of followed the robot such that we could get those rotary torques at the hip. It does come with a little force, which is why we cut the actuator magnet behind the robot at all times. But the key thing here that we were looking at is we wanted to see how changing the material, just the material in the leg, actually affected our ability to move in this case. Right, so what I'm showing you here is the black is a very kind of viscous viscoelastic material. Tango Black is a 3D printed material. It effectively acted as a rigid leg. So I get this kind of nice increase in speed, which is on your y-axis, versus stride frequency, which is how fast I'm rotating the legs here. I could create a material with higher stiffness and lower damping. This was like a Silgard 184, basically. And in this case, right, it's a soft material, but stiffer than the blue one up here. In this case, right, I get this interesting kind of behavior right around here, where I get kind of a peak point due to some interesting kind of resonances, and then it drops off. If I add a little more damping to this system, I actually get a little more stable locomotion at these higher speeds, which was really interesting to us, that actually energy loss, like actually not, thinking back on it, maybe is not so wild, but adding a little energy loss to your system obviously keeps you a little bit more stable. So this is, what this looks like. This is a 1x video. How fast it seems to be appearing out of thin air too, like it's magic. It does start on this side. It's just not showing it. There it goes, for some reason. So this could actually move pretty quickly over time. It was about 12 body lengths per second. But really, I was interested in going smaller. And so to do that, we used the same kind of nanoscribe 3D printing process. We could still make legs out of other materials and put them in very carefully with tweezers, not having had coffee beforehand, clearly. These are little 250 micron cube magnets, really small magnets that we buy from a guy named Super Magnet Man online. Also need to be careful about inserting those. And you end up with this little 2.5 millimeter long, about 1 milligram in mass magnet. So now we've gone from kind of a gram effective mass down 3 orders of magnitude to 1 milligram. And the question is like, at this scale, the hypothesis was now you have all this kind of joint friction, joint viscosity, all of these things are going to be affecting your locomotion differently than at the larger kind of 1 gram scale. And so, yeah, we were talking about earlier staged photos. Ryan liked to take a lot of staged photos with this, this ant right here as well. So in this case, we run this within a Helmholtz coil. We can actually get, something like 10 body lengths. We have a slightly different coil setup now that's bigger, so we can get something like 10 body lengths within this field. So we're generating torques at the hips, basically, in this system. And this is a kind of slower speed version of this at 1,000 frames per second. That was real time. It was super fast. So this thing, the fastest speed we were able to get was around 50 body lengths per second for this little guy. You can see it's a little bit chaotic, but a lot of it did seem to have, it wasn't, in this case, the compliance of the leg that actually mattered to us. It was actually more how the leg was interfacing with the ground. And so the material, effectively, you could think of the foot pad, seemed to be kind of the dominant feature. We have some separate modeling that I think is fascinating that's slowly getting out the door in publication that shows how those joint viscosities and frictions and stuff change as you scale down as well. They do start to become dominant at these kind of scales too. So you are ultimately limited by some of those features that you wouldn't even think of in a larger robot a lot of the time. It's also, this is wonderful. Like we just showed the Mars rock field. My rock field is I take some aluminum foil and I scrunch it up, and now like this thing can kind of go over that. So it, it forces its way through. It can handle some of this rougher terrain as well. So I think there's some interesting things here in terms of kind of material choice, leg design, foot design. All of these kind of things are going to come into play in how we design small robots to locomote. So I want to switch gears to the geometry, and this is a little robot that we had at ICRA this year called Zippy. This is a collaborative project with Aaron Johnson, who does a lot of legged robots. We both had small kids when we started this, and we were like, let's make a little Lego minifig robot. And so this is as small as we've gotten so far. It's kind of Duplo sized. I have some with me if you want to take a look of it afterwards. And this is big enough that I can carry it around and people can see it and I can make it run and all this stuff. So this is an interesting design. So in this case, we're looking at this control geometry axis in what we can play with. So this has a single motor, just one motor right here. But the kind of key design feature here is the shape of the feet. So the feet are curved, right, both in this plane for kind of roll and in your plane for pitch. And the idea is that I'm going to couple these kind of forward motion with the roll axis, and I'm going to be able to create enough clearance to swing my foot through for the next step. And so, this was actually, Stephen was a PhD student on this. Joseph and Soma were rising sophomores at the time who were incredible. So once it comes time for them to go to graduate school, I highly recommend them if you're looking for good students. Basically, it's as autonomous as the robots I make ever get, right? So it has battery on board, it has a little microcontroller on board, it's got a little sensor on board that we're not quite using yet. But this is the basic design of the robot. The weights on the arm are so that I don't yaw like crazy all the time. So they counteract some of that yaw that I get. So one of the interesting things with this is that we actually started from a larger version of this right here. And we shrunk it down, and it was okay, but not great. Like it kind of was on a little drunken walk across the video frame here. And the interesting thing that we learned from this is that, simply isometrically scaling everything is not the whole story. And there are some fascinating data that we've come up with recently, just looking at the literature and how robots scale, at least for locomotion. So if I ask you how mass scales with length, how would you say mass scales with length? Like as L1, L cubed, L5, what does it do? 3, L cubed, right? No, like for robots, it's about L squared. Bizarre. It's all about how we fabricate them and stuff as well. So I think there's some really cool stuff that might come out of that. But this was part of what led us down that path. Like isometrically scaling it was not enough. So what we quickly found is if we change the radius of those legs, of those feet basically, flatten it a little bit in the pitch direction, we could actually locomote much more cleanly, much better, much more stably. We didn't get these kind of crazy motions through here. So this was about 11 centimeters per second at 3.7 hertz. So this is 2.5 centimeter high legs, so pretty good. This is 1x speed. We can still turn, right? Even with a single motor, based on how you kind of control that motor. Like you can still turn right and left, and you can do so with different radii. mind-blowing to me is like, you did not need a perfectly flat surface for this thing to walk. So these are not huge steps. These are like 2.5 millimeter steps. We have our little terrain field for it to run on, and it actually ran outside as well on cement, which it even got over this little crack in the cement, which I don't know. If you had told me a little biped at this scale would work like this, I would have told you you were crazy a couple years ago. So this, I think, is really interesting to us in terms of how this thing moves. And then even more mind-blowingly, we got this interesting emergent gate. This is a skipping gate down here. It actually gets a flight phase. And a lot of this is due to how we've designed this system because we had to scale it down. So at the bigger scale, we have this kind of servo motor. You provide a little sinusoidal signal to it to move the legs, so everything's happy. At this scale, we just have a rather lousy motor, no encoder. We add a little hard stop in there to make it stop and go back the other way eventually. And this hard stop is enough to give it a little bit of momentum to get this kind of skipping gait in the higher stride frequencies. So this thing moved at about 25 centimeters per second, which is about 10 leg lengths per second. It could get over some terrain, very simple. One motor, which also makes it incredibly efficient. Right, so this thing could last for about an hour with the battery that we gave it, which at these speeds is effectively almost a kilometer of distance that it can travel, which once again, for me, I thought was super cool. All right, I don't have that much more time, so I'm going to tell you one more story where we're actually adding a little more complexity to these robots in terms of the kind of control that we can get at here. So this, I think, is dominated in large part by the geometry. The materials were the previous one. Here we're starting to add some more complex control. And so this is work by Suk-Jun Kim, who's on the job market this year. He's doing work with Tanya Morimoto out at UC San Diego on medical things at the moment. But in this case, the idea was, how can we add these kind of more degrees of freedom effectively in our small robot systems. And the magnetically actuated robot, right, there's one magnetic field controlling all of that. You can get different gates by how you put the magnets in there, but like we wanted to be able to change those gates on the fly. And so in this case, we're going back to that kind of that process that I talked about with the sensors where we 3D print something at the microscale, sputter metal on it. We can create actuators with that as well. So in this case, these are electrostatic actuators. They're actually, there's two of them right here. So there you effectively have two motors, servo motors right here because they rotate, right? Which is a little weird to think of from a microsystems thing. And we print these directly onto a flexible printed circuit board. So the idea behind this is that we can ultimately actually integrate some of the electronics and stuff as well in the end, which I think is sorely missing. So the whole thing here, this is about 8 millimeters in length and about 15 milligrams in mass. Suk-Jun also takes very pretty pictures of these things sitting on a leaf and the like. So here's the motors that we're using here. So these are electrostatic actuators. So they typically are a little higher voltage in this case. The robots typically worked at around 120 volts from what I remember. But in this case, right, you're basically creating a pure rotary motion. So it is a lot like a servo that we think of in larger scale robots. And you can get, depending on how high a voltage you add, you can get different kind of angular motion out of this. Right? The key thing here is that this is all printed directly onto a flexible printed circuit board, which adds some tricks kind of associated with being able to do that. But that ultimately allows us to integrate these kind of more traditional electronic components as well. And then these things now act as two servo motors at the base of this kind of 5-bar leg linkage. And so I can create kind of different patterns for my feet to go through that will help me with doing a traditional tripod gait. This is a hexapod robot here. Or doing a pronking gait where everything's kind of working together. I can do it at different frequencies. These electrostatic actuators are super fast, so I can operate them at a couple hundred hertz if I want. So there's a lot of kind of interesting benefits that we get of kind of integrating the actuators and the mechanisms together in this system. And then, like I said, we can get kind of tripod gait type stuff out of this, as well as pronking kind of hopping gaits out of this as well. And both come in handy at different parts. Like if you're trying to navigate some particular terrain, right, and I have to go over something, right, tripod gate is fine when it's flat, but to get up onto a slope, right, a pronking gate is actually really helpful for me to get through. It can move pretty quickly if you actuate it fast. So this is a robot kind of moving at a couple different speeds. Like that's about the fastest that it goes at the 250 hertz right there, which ended up being about 7 body lengths per second. So about 6 centimeters per second, so something like that. And as I mentioned, right, this is where that gate switching and that control gives us a benefit. So I run into this slope, right? It just kind of spins its legs, like it's not able to do anything. But now I can switch it to pronking. It's able to get all those legs in contact with the slope and keep going up with a tripod gate ultimately. And then this was around the time of the Women's World Cup last time. So we'll need to do a new one kind of coming up. So Jim painted some little Sharpie marks on a little 4mm foam ball and actually had this thing be able to kind of push the ball into the goal. So score, yeah. So I think there's some really interesting things here, even just adding some, one additional kind of degree of freedom per leg, like really allows us to kind of do different things in terms of gait and locomotion and that sort of stuff. So obviously we're using, this is the microdelta that I mentioned earlier, where we've got those same kind of actuators at the base. We're able to get crazy high bandwidths, like over 1 kilohertz with this little system right here. Interesting scaling questions that you can look at with this, given that there are a lot of microdeltas at big scales too. Really interesting and kind of continuing to explore some of the trade-offs in scaling down locomotion with a variety of morphologies, bipeds to hexapods, and even wheeled stuff as well. That's what we're looking at. So I think there's so many existence proofs, so many cool things that we can do with this, both inspired by a biology, but also like just our imaginations. And I think there's some potential big impacts on a lot of other fields ultimately if we're successful with this. So with that, I will thank a fantastic group of students who've contributed to this work over the years and a fantastic group of funding agencies as well. It's 5 o'clock, right? So I'll end with a cartoon here, and thank you very much for your attention. All right.